So what I thought I will do is, I also discussed with Professor Phatak, is there will be some part, the initial part which is introductory, and performance is a vast area. So going through each and every nitty-gritty is not possible in an amount of 2 hours. So the essence of it, what I'll try to cover is some basics of what do we mean by modeling, what do we mean by emulation, and then the second part I'll deal a lot with case studies, okay, which would be real life examples in very large distributed systems. The focus here is not on very highly sophisticated things. We are trying to look at simple things that are achievable in the industry, simple things that are long lasting for years together. And most of it, at the end of it you look at it and say, well, isn't this obvious? Well, it is obvious, but the time you have to apply it, it's never obvious, right? So it's common sense is more of, after doing it you say it is common sense. So that's the kind of thing you'll be seeing. Now before I get started, I want this to be somewhat interactive. So can anybody say, what do we mean by performance? Anybody? Concurrency, number of hits. So in more, broader terms, what do you say?
Measuring to expectation.
Measuring to expectation, that's a very generic term, right?
Even you can get the quality of service.
Pardon?
Even quality of the service to take.
Yeah, can you be more specific?
Execution time.
Yeah, so one is you'll have time aspects, right? So let's say response time, execution time. Second is in terms of what you said as hit rate. Now that's what we more often call as throughput. What's the rate that you're doing processing? So two essential terms that we look at. One is with respect to end users or end customers. There is response time. Okay. Which says is I want my transaction to finish in so much time. Either you can think of it as a business transaction. You go to an insurance company and say, okay, my policy will be created in 20 minutes or 15 minutes. Or you can have an individual page, you go to google.com and say I'm getting a response in 0.2 seconds, correct? Now that is from a customer perspective or an end user perspective. Now the business has to make its money, right? How do a business make money when it's having a certain number of transactions? So you go to Indian Railway site, they'll say, okay, how many bookings per day? Or you go to a manufacturing firm, you look at how many orders per day. So that is throughput. Okay. Now if I want to achieve a certain satisfactory response and I want to achieve a certain throughput, the business has to invest in some capacity, right? So that will be a servers, hardware, software, all that put together. So that's what we call the capacity side of performance, where we will decide how many concurrent users, how much is the peak throughput you have to sustain. And if I invest in capacity, I naturally have to worry about how much of it is actually being used. So that is the resource consumption or utilization part of it. So whenever we will be talking about performance in this next 2 hours, we will be meaning these 4 things. Actually, it's one and the same, depends on who's looking at it, right? The system administrator will only look at CPU utilization, database utilization, these things. And end user may look at response time, a business will look at throughput, and the CI will worry about the cost in terms of capacity. Now given this, what we'll cover today is a very simple kind of an outline. One is, what are the basics of performance modeling? So end of the day, when you're working on pen and paper or even before you implement your software, at the back of your head, you always have a performance model. Correct? The model is always of some type. Because in reality what you see and what actually happens in your thought process is not always necessarily the same. So you start out with some model. And the entire course of modeling, it takes about 2 semesters in the college. That we'll try to compress into almost 45 minutes. So we'll not go through the entire gamut of modeling. But what are basics that are applied universally? We'll see case studies there also. So that will be sample applications of modeling. The other thing that I'll try to introduce, that's a new concept, but it's gaining a lot of momentum. It's not that it was not there in the past. The way it's being used is pretty useful. So everybody has heard about virtualization. Now what do we mean by virtualization of performance? And why it is useful, that also I'll talk about. And then the second part will focus a lot on real life examples. That, as I said, these are common sense examples of large systems, distributed systems, architecturally what are the best practices you can employ, especially when you're dealing with your service-oriented architectures. Okay? Now, when we get on to the basics of modeling, what I will talk about is a simple thing that we call operational analysis, which means is think of, and whatever I'm talking with this part on modeling, it actually applies to any system. Could be a computer system, railroad system, your roadways, airport, cafeteria. Okay? Now think of a system as a black box. you are, let's say, a security guard downstairs who is only observing what's happening to the system from the outside. Okay, you don't know what's going on inside. So suppose you take the room as a system, somebody outside doesn't know what each of us is doing. So what are the events that somebody from the outside can observe? Anybody? I take any black box system. As I said, it could be a network switch, it could be a data center, it could be this room, it could be the airport, it could be an entire city.
Entry exit.
Entry exit, very good. Okay, so I'll observe two things. One is who's coming in and who's going out. Okay, so whenever somebody comes in, I will add 1 to the counter. I'll say, okay, the blue curve is the total number who has come in up to some point in time. Now we also keep a very simple assumption that two arrivals at the same time occur with probability 0. And if they happen at the same time, I'll say, okay, one happened at time t, one happened at t plus delta t. So I can always say that they are spread out. Now likewise, the other event is somebody leaving the system. That is the red curve, which says is this is the total number of departures up to some time t. So I'll measure over a period of time. Now we are assuming that the systems we are talking about are work conserving. That means there is no work being generated within the system, there is no work destroyed in the system. So if you take the room, we'll say nobody is born inside the room and nobody is dying in the room. So that is work conserving. Okay. Now given this assumption, can the red curve be more than the blue curve at any point in time? Anybody? Correct.
Yes.
Yes, when will it be more?
At the last of the activity.
Pardon?
At the last of the activity, do you know?
Why last of the activity? We are talking total arrivals, correct, and total departures. So it cannot be, right? You can't have more departures than arrivals totally. Now what happens when they intersect? What happens when the curves match?
Few people are coming in and few are going out at the same time.
No, we are talking of, say you take total number in this room, right? So when they intersect, what does it mean? Let's say there are 0 people left, correct? So whoever has come in has gone out, correct? So that is, there is nobody in the room. Now what is the difference between these two? So if I say, okay, there are 100 came in and 50 went out. So what's the difference between the blue and the red? Whoever is left in the room, right? So this is what we call a number in the system. Now this number in the system is a function of time. It will keep varying over a period of time, correct? Now whenever we get into performance in general, we tend to look more at averages. So I want to know is what is the average number in the room at any point in time, correct? Now how do I get the average of a function? This is a function of time, right? How many of you have done mechanical or electronics background in your bachelor's or master's, right? Okay, let's say I give you a signal, a function of time. Now I tell you, okay, you measure it over 10 minutes. How do you get the average value of the signal? Now let's take temperature in Bombay, right? So how do you say what's the average temperature in Bombay? Well, you add it up if I have a discrete point. Right? Suppose I have a continuous function, then what do I do? What's the analog of addition in continuous space? Keep it simple, okay. Suppose I have to take 100 samples, I'll add them up and divide by the number of samples. That's how I get an average, correct? But let's say I take very, very small number of time intervals and I add everything up. So in the continuous space, what is that called? Integration, right? So when I want to find the average of a function of time, what I do is I integrate it and I divide by the time interval. Okay, now if I go more along integration, most of you will leave the room. Okay, so we will not spend more time in integration part of things. But if you look at integration of a function of time, any function, pictorially what does integration mean? Area under the curve, right? So we want to find out the area under this curve, correct? Now this area is a set of area of rectangles, correct? What's the height of each rectangle? We said whenever somebody comes in, we add 1 to the count, right? Because that's the total number of arrivals, total number of departures also. So what's the height of the rectangle? 1, correct? Because we are just saying we are incrementing the count by 1. Now what's the width of the rectangle? So you say, okay, somebody came in at some time, somebody left at certain time. That's the duration, or what we will call as response time, correct? That is response time under one assumption. What's the assumption that we are saying is that this will be response time? Response time means I came in at time 5 minutes, I left at time 10 minutes, so my response time is 5 minutes, right? But under this thing that we have drawn up here, this will be response time only under one assumption. What is that?
Say, number of in and out are equal.
Well, not necessarily in and out are equal. What this we are looking at is if I have the same sequence of departures.
First in, first out.
Exactly. So it has to be first in, first out. Then I can say it is response time. Otherwise it could be okay, I came in second but I left first. They are not matching, correct? So for now assume first come first serve. Second slide will show how does the same thing apply without first come first serve. So this area that we are talking about, we are saying is we add up the sum of these response times, multiply by 1, that's the area under the curve, correct? That's the equation 2. We want to find the average number in the system. So we take this figure, add up this, divide by t. This right now will make no sense. So what we'll do is we'll play a simple trick. We'll divide and multiply by the total number of departures, correct? So we say, okay, you measure the interval of time, let's say 30 minutes. There were, let's say, 500 jobs that completed in 30 minutes. So I take this and there were 500 samples. So what's the first term? Which means this total departures that have number of completions divided by the time interval you are measuring. So what is that term? Let's say 500 jobs finished in 30 minutes. So that is throughput, correct? We had said what's the rate of completion. What's the second term? Which is total of response times divided by number of samples. Okay, give you 1000 samples, you add them up and divide by 1000. So what is that? Average, correct? So this is average response time. So effectively what we are saying is, this is what is the most common theorem in performance modeling, what is called as Little's law, which means there is the average number in any system, any work consuming system, is the throughput times the average response time. And this is probably the most universally used equation in performance modeling because it holds pretty much without any assumptions, correct? Now there is only one assumption, so just so that we put it to rest. If it is not first come first serve, then how does the same thing apply, right? So it is some departure time minus some arrival time. Now if you look at this, even if it's not first come first serve, there has to be some pairing, right? So there will be a one-to-one correspondence. That somebody arrived at time A1, that person left at time D2. Second person to arrive was the first one to leave. So there is some pairing. So what we will do is, we will just renumber these departures. So whatever I call as primes, D2 prime is just corresponding to the arrivals. Okay, that means now when we talk of response time, we are talking of response time as this prime minus the arrival time. Okay, that's the way we just renumbered them. Now if I look at this bottom part, okay, the shaded area, we are saying it's the sum of all these timings. So summation is a linear operator, that means I can just add up these sums. Once I add it up, I can shuffle it in any order, the sum remains the same, correct? So that's what this will be. Once I do it in this way, I can repair it. So that what I get is the response times. So essentially what we are saying, it doesn't matter what is the sequence of departures. This shaded area has to be the sum of response time. So Little's law will hold regardless of my sequence of departures. Now effectively when you are using Little's law, you can use it in a variety of circumstances. So you mentioned about hits, right? Concurrent users, HTTP sessions, hits. So you can say, okay, average number of HTTP sessions in my web server. Or if I look in a database, I can say what's the number of concurrent SQLs that I'm dealing with. Or I go into the canteen, you can say what's the average number in the canteen. Or if you're dealing with even project management, you can say I'm dealing with an average of 5 projects at a time. The time it takes me to complete my project is response time. And the number of projects I complete per year, that is my throughput. So all this you can apply Little's law pretty universally. Okay. Now this is one part of the theory. There is just one extension to Little's law which I just want to cover also. When we talk of many systems, see at a component level you can do this. If we have actually systems where we have a lot of end users as part of the system, then what we do is we just draw the boundary around the users themselves. So let's say if you're dealing with a campus, there are 500 people in the campus who are logged into the system. So I'll say, okay, if this is my boundary where I include the users themselves, then from a user perspective, there are two things, right? One is I submit a request, I wait for a response. Or I could be even typing it a request. I could be seeing my previous response. Let's say I'm creating an insurance policy. I may have 30 steps, including typing in, seeing the response. I may drink coffee, I may go to the toilet, I may do whatever. So all that is what we call as think time. So either you're spending time in the browser or you're spending time waiting for response. Okay. So now in this case, my entire completion time is my response time plus think time. I know my number of users and I apply Little's law to this closed system. And that is what Little's law will apply by saying is my number in the system is throughput times response time plus think time, because they are dealing with completion times. Okay. Now this is one part of modeling. The other part which I thought I'll get out of today first thing in the morning, because as we progress, people don't like to get into mathematical things later in the day. So we'll cover that while all of you are fresh. The other thing that happens a lot in performance is how do you analyze for bottlenecks, correct? So let's take a simple example. Let's say you are manufacturing a car, it's an assembly operation. So it goes in a set of stages, correct? Now when we say assembly, it means that if the first person is in the second stage, I can have the second person in the first stage, and the entire pipeline can be full. So at any time, a single car will take 8 minutes to come out, correct? If I did not have pipelining, my throughput would be only one car every 8 minutes, correct? If I have pipelining, what's the throughput I can get? Louder. One car for 2 minutes, okay? So I'll have 4 cars every 8 minutes with the pipelining. So that's the kind of efficiency I can get in throughput. However, in real life, nothing is as well balanced, right? So whether you're dealing with a project, whether you're dealing with an assembly operation, always there will be imbalances. So let's say the guy who's at the door is a lazy person and takes 4 minutes, correct? And now you have a situation where you have a car coming out every 10 minutes. But what's the throughput now? How many cars every 10 minutes? 4 cars every 10 minutes? Okay. So let's take a related example. Maybe I should have shown this earlier, right? But lunchtime it works very well. Okay. So this is also a pipeline. You go to a McDonald's or any fast food joint, correct? And you say, okay, if the pipeline is full, I will do one order every 20 seconds, correct? Now let's say to prepare a burger, okay, let's say veg burger so everybody can eat it, it takes 30 seconds instead of 20 seconds. So how many burgers per minute can I do? 2 burgers per minute, correct? So that's one thing I've learned in the last, 10 years. And whenever you convert the example to food, the problem statement to food, you get the answer very quickly, okay? So you go back here, and you will see you cannot do faster than 1 car every 4 minutes, correct? So that means your bottleneck stage is the one that determines your maximum throughput. You cannot do faster than the slowest stage in your pipeline, correct? Whether you have a speed breaker, whether you have a slow team member, whether you have whatever, you cannot do faster than that. Now then you may say, is fine, this is for pipeline systems. But if you deal with any distributed system, any service-oriented architecture, it's not necessarily a pipeline, right? It could be more complex. So why should we deal only with pipelines? Okay, that will be clear in a moment. So let's take, suppose you have a more complex architecture. So you have, this is just a sample. I'll not get into trading systems or whatever. But you will have things which are never a pipeline. Now how do you analyze these systems? So what you do is, you say is, let me take any generic architecture and I say, okay, here are my users, here are the business transaction. For every business transaction, I look at 2 things. Any component, how often do I visit that component? And every time I visit that component, how much time do I spend in service at that component, correct? So let's say here is Professor Umesh Bellur, richest person in Bombay. What a salary of 20 crores from IIT Bombay. Since he's so rich, I ask him for a loan that, okay, give me 20,000 rupees, okay.
He is asking me to fix that salary.
So I want a loan from him for 20,000 rupees. So I can do it in many ways, right? One is, since he's rich, I'll go to him once and say, Umesh, give me 20,000 rupees. So that is 20,000 rupees. Or I can go to Umesh 10 times and each time borrow 2,000 rupees. Correct? Total is still 20,000. So that's where you have visit count and you have service time. But what really matters is the total that I am borrowing from Umesh, right? So what the total is, how often do I visit somebody and how much time do I consume in service? If I multiply these two, I get the demand. So what matters is the total demand, not necessarily the individual when you're talking of the averages. Okay. So I am keeping it simple. See, there are always technicalities which we are skipping. So there are references which I'll speak about later on. But the essence is this. Okay. Now once you convert into demands, it doesn't matter where Umesh is sitting, right? It could be anywhere in the pipeline, and still the total demand is the same one. So therefore, once you convert to demand, what we've done is we've converted the whole system, however complex architecture it is, into a pipeline of demands. Because the moment I talk of demand, my visit count is once. Correct? So now if we take this particular example, you take the red one, okay? Red circle, what is the demand? The visit count is 2.5, average service time is 2. So demand is what? 5. If we take, the purple one on the right, 4 and 0.5, what's the demand? 2, okay? So we convert it into demands, we get it this way. So now what is the maximum throughput I can get out of this? 1 over 5, right? So my maximum demand is 5, I cannot do faster than 1 over 5.
But sir,
Yeah?
it would depend on efficiency and capacity of the system, not necessarily demand may be more.
All that is counted when you count the time, service.
See, when we are talking of this, see, we assume Umesh has infinite capacity, right? That was the first thing. He's the richest person, so 20,000 is not a big deal. But in reality, when we look at visit count, that is a function of your architecture, correct? So based on how you architect the elements, you'll have a certain visit count. Service time, in turn, will depend on how fast my processing is. Now, visit count also depends on the deployment architecture. So let's say I give you 12 CPUs and I have a web server. Then my visit count to each CPU is 1/12. And my service time, so my visit count automatically gets adjusted with capacity. Correct? Service time will depend on how fast the processing is. So therefore, when you talk of demand, as Professor Phatak said, this is subsumed in this equation. Okay? So now we say, okay, no matter how complex my architecture is, I will not do faster than 1 over the maximum demand. So that is my bottleneck throughput. Okay? So therefore, no matter what system I have, upper bound on throughput of that system is 1 over the maximum demand that I can have. Okay? Wherever it is, it could be, I could be locking somewhere and therefore I cannot use capacity, or I could hit a capacity bottleneck and I cannot go faster. All that is dependent on what my demand is. Now this is throughput. Okay? We are also dealing with response times. So when we talk of response times, we use Little's law. Correct? And we say, okay, Little's law we covered based on if I have a think time and response time. Now if I have an upper bound on throughput, what does it become in response in terms of response time? Does it become upper bound or lower bound when throughput is in the denominator? So you look at this equation, I substitute that bound on throughput in the response time equation. So that will convert to an upper bound or lower bound in the response time. It will be lower bound because it's the denominator, right? So I substitute this and you will say that my average response time has a lower bound of what we have just spoken about. Now, intuitively you want to think about the lower bound on the response time, just think of it. If I have a bottleneck, then think of it as if all the queuing occurs at the bottleneck. So therefore you have n times that Dmax. So everybody is queuing behind it. So that is an intuitive way to understand it. Okay. So all this is clear. Okay. So we'll take a few examples which will refine it. We are not having a quiz, so don't worry about that. But if you want one, I'll be happy to conduct one. Okay. Okay. So let's see how do we apply these things. So let's take simple examples. Okay. Now this happens a lot in IT firms. Very often a client will come, they will give a requirement. Sometimes requirement may not always be clear, but assume that you got a requirement. So this is one prime example. So this is, nowadays everybody talks of program trading, where there are not humans who do the trading. So it's coming to India, it's just the legal part is still not through. But you take many of Japan, US and so on, it is software that will observe the market and automatically place orders to the stock exchange. So for example, I give you Bombay Stock Exchange and National Stock Exchange, correct? Let's say you take TCS stock is what, maybe 875 in Bombay Stock Exchange, maybe it is 870 National Stock Exchange, correct? So there is a 5 rupee difference. Now what I can do as a software, I'll observe the price and I'll say I will buy from NAC at 870 and I will sell in DAC at 875 and make the 5 rupee difference. All that I can do automatically. So that's where having a program, the decisions are made much faster if the rules are simple enough. Now, typically in program trading, you take Japan, US, whatever, you have a very high throughput. You have thousands of orders per second. Response time have to be in very, very sub-seconds. Okay. So let's say somebody says here are 10 program trading terminals. I want average response time 100 milliseconds. I want throughput of 1000 orders per second. Now the state of the art in the industry is you take this, you architect a solution, you build the capacity, then you will start developing it, then you will test for it, and only when you come to testing, you realize that there are some performance issues. That's the first thing. Okay. Now in these cases what happens is, normally when you do testing, your target is 1000 orders per second, you will end up getting 2 orders per second in the first round. Okay. Anytime, anybody who does performance test will notice that. Then you will do some tuning, design optimization, code optimization, you will go to 20, 30, whatever. Then after some point you will realize, well, I cannot meet this. So you will go to the customer and say, well, this is not possible, I need to add capacity. So if they are Wall Street firms who want to get the answer as of yesterday, they will say, okay, you buy capacity, put it in. Now in these cases, I am guaranteeing you, no matter what you do in life, you will never meet the requirement. Okay, so because the requirement is flawed to begin with, it is not something which can be achieved no matter how much effort you put. Okay, why is it flawed to begin with? Because it's not in compliance with the physics we just stated. Correct? So if you apply Little's law, you will say, okay, I have n as 10 terminals. My throughput is 1000. Average response time is 0.1. And think time I don't know, but it has to be positive, okay, cannot be negative. So this will never be met. Now you may say, okay, this is just a target was 100 milliseconds. So I could have always done some optimization. So I could make my response time much less. Now how much less can you make it? Even if I make it 10 milliseconds, I'll just about meet it. But if I take from a brokerage firm to a stock exchange, my network latency at least will be 10-20 milliseconds. So this is something I can never meet. And these are things which you have to get upfront right at the start of the project. Because you cannot expect the client will always be right. Correct? And you cannot expect that the developer will always right and meet any absurd requirement. Okay? So these are things which are called for requirements analysis, where just a 5-minute analysis, you can correct a lot of damage. Okay? Now let's deal with some other types of requirements, which happens very often. You have some service you are having, it's running fine, until one fine day somebody comes and says, I also want to eat into it. Correct? So this standard thing, let's say, happens in databases. I have online transaction processing going on quite smoothly. Over a period of time, people want reports. So they will fire ad hoc reports, ad hoc queries. Now you may say as well, it's high time I build a separate data warehouse, I build a separate reporting system. But very often clients will feel is, well, there's no budget for it. You prove to me whether it's really required. Correct? Now the challenge you will face is very often is that if I am doing measuring and monitoring of the system, any database you take, Oracle or whatever, the process name remains the same, right? Looking at the utilization of the process, I cannot figure out whether it is serving reporting queries or online queries. So am I supposed to know what's the interference because of reports, correct? So what you do is, most of this you want at a macro level, you don't want necessarily fine-grained level. So what do? You say is, okay, whatever we talked about Little's law, does it apply for each stream? So if I take the pink stream, let's say I am colorblind, okay? Colorblind only in one color, I'll put on pink glasses. I put on pink glasses, I don't see blue at all. Will Little's law still apply? Or I put on only blue glasses and I don't see pink at all. Will Little's law still apply? Only for that class. Yes or no? Okay. So the answer was no, I would not put this up. Okay, just to save time. You work out the same derivation that we did. It has to apply also for every class. So it will apply for the blue stream, it will apply for the pink stream. Okay. Now if you go with this and you say, okay, suppose I have got requirements. I know that I have done my design, my online will take 2 requests, my report will take, let's say, 50 database requests. Okay, rest of the stuff, number of users, response time, think time, that's a given. Using this, can I tell you how much is the interference because of this other service that is being introduced? So what you do is you apply Little's law and you get the throughput for every class. Right? So you say, okay, I have n as 1000 for online, divided by response time 5, think time 5, so that is 100 online transactions per second. Likewise 2 reports per second. Now if you go and show this to a customer, you'll say I told you reports don't matter, correct? And you may feel why the hell did I do all of this just to shoot myself in the foot. Because as I said, what really matters is the intuition you have behind it. If you feel it will interfere, then you have to prove it interferes, correct? So what you really need to worry about is not this side, you have to worry about how many requests come on the database server. So you multiply with the visit count. Now when you multiply with visit counts, you will see that I have 200 online requests per second because of 100 online transactions per second multiplied by 2 database requests per second. Likewise, I have 2 reports per second. Each report has 50 requests. So I get 100 per second. Now you take any reporting system, the queries are more complex than online processing. So therefore, even without doing any further measurement, I can say your reports will eat up at least 30% of capacity. Correct. So all this I can do without necessarily taking measurements, just by getting the external entities and then seeing is it going to have impact or not. Another thing that happens very often in any performance system you deal with is sometimes, without your knowing, things will start choking, and only when customers start complaining that you start seeing something is going wrong. Okay? So you could have systems which is very often, you take many large systems worldwide, there will be a back-end legacy mainframe that is working great. Somebody puts a middle tier and says, okay, my transactions are going fine until one fine day it chokes. Okay? So because of capacity or whatever reasons, I am choking at 25 transactions a second. As my number of users increases, my response time gets worse and worse and worse. Okay? So now you have a situation wherein my response time has gotten to 60 seconds. People are complaining. And the target they want is less than 10 seconds. Correct. So I want 6 times improvement in response time. So how do I get it? Now the very naive way of thinking is, I want to go from 60 seconds to 10 seconds, I just throw 6 times capacity. Correct. Now is it going to work? We don't know. So what's the normal way in which the customer says, well, I want this? The first thing that people normally will say is, well, let's test for it. Okay. Now it's a very nice word, let's test for it, because first thing that you have to do is you have to say, okay, develop the testing scripts, get the hardware for it, then you have to run it for a matter of few weeks, minimum 1 month. So for services company it's good revenue, right? You get consulting revenue, let's test for it. So we are saying is, rather than wait for 1 month, here something is burning. How do I fix a fire quickly? Correct. See, if I have to fix a fire, let me order infinite capacity, I don't have that much budget. If I order only 1 server, it may not be good enough, because then it takes 4 weeks to procure the next one. So how do I decide what's a good ballpark? Correct. How do I decide what's a good ballpark? What we learned today is a very simple analysis. Let's say if you have some architect who says, yeah, there is scalability in the application. This bottleneck that you got, wherever it was, doesn't matter. Your throughput is 25, that means the maximum demand at that tier is 1 over 25. So it's 40 milliseconds, we don't know where it is. Correct. Then you say, okay, what is the think time outside of this application tier? Work out this math based on the equation. You'll say it's mainframe time plus think time total is 20 seconds. And now you do the what if analysis around the model. Okay. So you say, okay, I want to know how many servers should I add to bring my response time down to 10 seconds. So you say, okay, what if I had only 1 server? That's what we started out with. Your response time will be at least 60 seconds. What if I had 2 servers? If I had 2 servers, in best case, I will have my visit, so the requests go to either server. So my visit count becomes half and my demand becomes 20 milliseconds. That means my response time has to be more than 20 seconds. Otherwise, I am telling you without doing any test that if you add a second server, you are never going to meet your response time requirement. So don't waste your time running for this case. And then you say, what happens if I had 3 servers and do the same exercise? And you say response time is greater than 6 seconds. What's the exact value? I don't know. That's more advanced queuing theory you can get into. But on the ballpark, I can say you start with at least 3 servers. Rather than saying is, okay, put the 6 or put 2. So these are very simple ways you can do a very quick and dirty analysis to say what is your capacity required. Yeah?
Our experience is that user never come up completely with his requirements.
Correct.
Even we do URS, SRS,
Yes.
his signatures also.
Correct.
But when you show him the prototyping or something, you know, I forget this thing, this should also be a very critical thing, it should be part
Correct.
of our system. But if we do prior infrastructure prediction, like what should we look like, then whole thing. So always we plan for the some 20-30% higher capacity so that
Correct.
if such things come, we should take.
Correct. No, what also happens is you will plan on prior capacity, right? But when the user workload increases, very often it doesn't increase without, it doesn't say that I'm going to increase, correct? So I may have a 5-year budget, I've already exhausted in the first year, then what do I do? Correct. So you will find the situation n number of times wherein there is a trade-off between saying, should I optimize? So normally yes, you must try to optimize within the capacity you have. But if it's going to take me 3 months to optimize, what do I do in the 3 months? I need to rent out capacity, I need to do something, and that time customers want to know is how quickly can I get that hardware and what should be, correct? So these are things to very quickly get an answer. How much is the additional capacity required? Whether you use it for a short time or long time, that is secondary, correct? Sometimes you may say, okay, if these are commodity servers, it's much cheaper to add commodity boxes rather than spend a lot of time in testing and analyzing, correct? Okay, so these are about, simple ways. As I said, I will not be very exhaustive in this way of doing the analysis. Now, before we take a break, one last part I will also want to share with you is, all of this we have spoken about is with respect to doing analysis from an architecture perspective, requirements perspective. So you may do a great job in architecture and requirements, okay. But the real work when it comes to implementation is done by a set of developers. How do you actually work with them? Now, this we can discuss offline. There are ways in which, using the same theory I spoke about, how do you translate these end-to-end requirements into targets for developers? So let's say you do that also, correct? However, a developer is always on a very nice environment, which is having, let's say, very few users, very small number of rows in the database, and a nice 1 Gbps local area network. Okay, all the fire is there in production, where you have very large number of users, very large database, wide area networks, whatever, okay. Now what we want to do is, if we start getting into modeling and teaching developers modeling, it's going to be a disaster. Okay, so we have to try to say is, can I bring the production environment to the developer? So in some very few cases, people actually do it, it's very expensive. So that's why we're talking of a virtual production environment, where he says, okay, something which we are trying to make as a USP in TCS, but some parts we also released to open source. Okay, so I'm talking about that part only that we released to open source. Verbally I'll talk about the other part we're working on. So what you do is you take a standard environment. Okay, so let's say 99% of all your applications have app server, database server, local area network. Can you put a ring around this to make it appear as if it's a production environment? But you need to do it in a way that does not change the development process. Okay, it should not cause any other extra learning for the developer. Then it works fine. Okay, now if you take today, at least my experience has been, when I did programming and we did our studies in the 80s, 20 years from now, the people are much smarter than we were. They are used to more technology. And the moment you give them proper requirements, they will do amazing things to get to that requirement. Correct? So if you give them a requirement that you need to finish in so much time, you give them an environment which they don't need to worry about, it's there in front of them. They will find ways of optimizing. So optimizing is not the solution. You need to give the requirement properly. Okay? So what do we mean by virtual requirement? We are saying is, you take a standard development environment and you take a production environment. This gap is so huge that pretty much all the large projects run into fire because of this gap. Okay? Simple thing, I put a firewall, connection breaks, I have no way to respond to it. I have a very low bandwidth over here, there I go for 1 Gbps, I always run into trouble. Okay? So what we are doing is, we said let's take one component, which I'll show you right now. I want to bring the wide area network over here. So rather than saying is, you be a network analyst, you take measurements, you do all this, which is not going to be that acceptable. All we'll say is, we'll put an emulator. So we will give you a CD, okay? It will just boot off, it's an OPEX CD, it will boot off a PC or a laptop. This is plugged into your network, and then with a simple command, okay, that it's like how do you set your IP address for a gateway? You will just add a route from desktop to here and from server to here. Even the second part is not really required actually, and we just put some netting if you want to do it. Once this is in place, okay, then we give you controls. So what you can say is, I want to have, even though I'm on 1 Gbps LAN, I want to have only 128 kbps of bandwidth. So you can set a bandwidth control. I can say I'm working on a satellite link where I'll have 500 milliseconds latency. So you can say this is my latency. I want to test my software for robustness. So I can say this is the percentage packet drop. I can say at times my connection will get disconnected. So I can put disconnects. Okay. Once I do all of this, remember these settings are done externally, right? It may not necessarily be done by the developer. Once it is done, then every packet that you send is going to be slowed down accordingly. Now see what's happening, right? What matters in every software project today is not performance, not necessarily 100% correctness, is a time to market. I have to deliver by next Wednesday, I have to deliver, okay? So let's say I have so many days to deliver. Normally what's the cycle? The first deliver, बाद में देखा जाएगा. That's a standard approach. So you say, okay, if I put this within your development environment and you have to deliver a software by next Wednesday, you have no choice but to optimize during development. Otherwise your development process is so painful, correct, that you will never release your software on time. The moment you know that I am running out of time, then you start thinking of should I switch on compression, should I reduce latency, should I put some caching on the browser, app store, what is required. You will get ideas because it is constraining you. So if you look at in 84 when we used to do programming, in IIT Bombay we used to have a Russian EC1030, okay, punch card system. Now while we may complain about it, one of the good things in those days was that the programs were almost always right. Because we are forced to write on a paper. We had only some 64 kilobytes of RAM and we had 24 hours of turnaround time before we get the compilation output. Okay. Now because of that, when you operate under constraints, you will operate so well because you know what the constraints are. Okay. So all this is doing is it is putting the production constraints in development. Now same thing I can also do when I am doing normal testing. You do unit testing, use system testing. Without changing my testing process, I can tell you about end user experience. Correct. Now you may say, okay, I am not a network expert, how do I set these values? So what we also provide is a WAN characterizer, which will sit on one side of the link. As long as you can reach a remote point in your network, that link it will automatically estimate these properties and will plug them. And because I do it on IP, even below TCP IP, pretty much all technologies automatically get supported, correct? So whether I do it in testing, so we use it in a number of ways. As I said, we released to open source. So you can go to the site vanm.sourceforge.net. Since July last year, we've had almost 8,000 downloads of the tool. And a lot of people in the open source community have also given feedback on it, So it's improved in quality thanks to the feedback there. So we've used it in a number of ways. So one is I can use it for sizing, correct. Now when we do sizing where non-IT people do the sizing of networks for us. So for example, recently we had a large bid, okay, New India Assurance. Now customer said, I want to know what's the bandwidth required per branch. So per district office, regional office, whatever, correct. Now normally what's the process you will follow is, you will run through your policy creation, claims creation, you'll put some sniffer, you'll get the network bytes in, out, do a lot of analysis, okay, that's the normal way. But very often, sometimes you're struggling to deliver a proposal today that was due yesterday, okay, always in fighting there. Now if you go through a lot of detailed analysis of the program, it's going to take a lot of time. If you want a faster way, what we do is, we say, okay, set it up in the desktop or laptop, have an insurance expert, just keep filling up the claim or policy. So that is some 45 steps we go through. And what we do is, we just grab that person's traffic through VANM and we keep dynamically reducing the bandwidth until that person screams, this response is too slow. So then we say that's the bandwidth that you require per user minimum. Okay, so there are ways in which you do network sizing. We've had cases where people in production get problems. So how do you reproduce their problems using VANM?